Okay, 1 and 2 students, let's try another solution here. Here's the problem 19 from chapter 11, and it has to do with the ideal gas law. It says here a helium bottle, and so maybe I'll make a bottle filled with some helium gas. So here's helium under a lot of pressure. It says under 100 atmospheres, and it has a volume of 2 liters. Okay. It says how many balloons can this bottle fill up if each balloon has a volume of 1 liter and a pressure of 1.25 atmospheres. All right, so we know for a gas this is always true. The pressure times the volume equals the number of moles, or we'll call it number of molecules, times some constant times the temperature. So we might do something like this. A very useful way is to put things that are going to change. So if you start filling up a balloon here, the pressure is going to drop. But also, as the pressure drops, we fill up a lot of balloons. So the volume for these molecules that are in here changes. So those two are already together. Now, as we do this in a room, we're not going to change the total number of atoms. They just get distributed a little different, okay? And we're not going to change the temperature of them. We're going to, leave them in the room. It's not going to go outside or, where it's hot or cold. So you might say something like this. Maybe call it P initial, volume initial. So that's what it's in the bottle, equals to nRT. But then also, after you open up the bottle and let them out, they're going to be under a new pressure, so I'll go final pressure, and a new volume, but it's still going to be the same number of molecules and the same temperature. So the idea here is take the ideal gas law, put the things that vary on one side, the things that don't on the other. That way you can say all this stuff that varies is equal to a constant, and then so as it varies, it still equals that same constant. So in this case, we could say that the initial pressure and volume multiplied together would equal to the final pressure and the final volume. That was actually discovered by somebody named Boyle, so we often refer to this as Boyle's law. Not sure the name is important, but the idea here of the math is, and so what I'm going to do is I'm going to take the pressure that we start with, okay, so 100 atmospheres of pressure in a volume of 2 liters. And then we start filling up these balloons. These balloons are at a lot lower pressure and about 1 1/4 atmospheres. Kind of makes sense. This would be the pressure, 1 atmosphere. So it's a little more than atmospheric pressure. So you got the rubber on the balloon pushing in. And then the volume. So basically we're saying if you take a small volume at a high pressure and you let it out to a low pressure, what's going to be the volume? All right, so grabbing my calculator here, I would take the 100 times the 2, that's just 200, and divide it by 1.25, and we're looking at 160, and if you watch your units, atmospheres would cancel, and so we're looking at 160 liters. So again, if you let all this out into a bunch of balloons, all these balloons would add up to 160 liters. That's kind of what it's saying here. Now, we know that each balloon is 1 liter, so we are going to have then 160 balloons. And I probably should be a little more strict. Maybe I should go back and look, but I looked in past semesters, and I believe the author leaves 160, and that would be fine. But truth be told, the volume now at this pressure would be spread out at 160, and 2 liters would still be left in the bottle. You can't get all of it out. You can't get, zero pressure in here and it go into the balloon. So as you use this tank to fill it up, the tank's going to drop down to a pressure of 1.25. And at that point, you don't have any more pressure to put into the balloons. So there's going to be some left in the tank. So I would say the first 2 liters are really in the tank. So the number of balloons is 158. And I think the 158 is a little better answer. But I do think I remember the solution putting 160. I'll take either one because it still is requiring you to do this step. And that's the big step, the ideal gas law, the connection between pressure and volume and temperature and the number of molecules. And then how do you look at something before and after? All right. That's the gist.